The next topic we want to look at is why the sky is blue. And that has to do with the way that the sunlight interacts with the Earth's atmosphere. Now, the light coming from the sun is white, which means it contains all the colors of the rainbow. But the size of the air molecules is such that blue light interacts with it most strongly, and when the blue light interacts with the atmosphere, it scatters in every direction. Whereas the red light can only be seen coming from the sun. Now, it turns out that the amount of scattering of the light is proportional to the inverse fourth power of the wavelength. Here we see proportional to 1 over lambda to the fourth power. That's what that means, where lambda represents the wavelength of the light. Now, if you recall, blue light has half the wavelength of red light, or 1 over 1/2 to the fourth power. That's the amount of scattering. That's how much more scattering the blue light gets than the red light. So when all is said and done, what that means is that blue light gets scattered 16 times as much as red light. And so that blue light is being scattered in the atmosphere in every direction. So if you're up on the moon and you look down, the Earth looks blue. If you're on the ground looking up, the Earth looks blue, because the air is scattering all the blue light the most. Next, we want to look at the question, why are sunsets red and orange rather than blue? Consider a position on the Earth right there. Now, when it's noon, the sun is directly overhead. And when the sunlight comes down, it goes through a relatively narrow portion of the Earth's atmosphere. So all the while the sunlight is passing through the atmosphere, it's being scattered out as blue in every direction. Now, when the sun is on the horizon, the sunlight comes through a much longer path of atmosphere. And so there's scattering of light in every direction. The blue essentially gets scattered out. It gets scattered out by the atmosphere, it gets scattered out by the dust and other things, and that is why the sunset looks red and orange, because all the blue light has been scattered out over back here, and when you see the sunlight there, it looks like the colors minus the blue. And depending on what's left in the atmosphere in terms of dust and particulate matter, you'll see different colors on different days. But that's why the blue does not dominate when the sun is on the horizon. When we look at the history of the Earth's atmosphere, it's actually pretty complicated. When the Earth was first formed, the atmosphere consisted primarily of hydrogen and helium, which are very, very light gases. Now, it turns out that the speed at which a gas moves in the atmosphere depends on its temperature, and it depends on how massive it is. Hydrogen and helium are not very massive at all, so they move very, very fast. In fact, they move so fast that they essentially move faster than the Earth's escape velocity. If you remember, we talked about the escape velocity as the velocity something needs to escape the Earth's gravity. So any hydrogen and any helium that's in our atmosphere will eventually leak off into outer space. It will escape the Earth's gravity. Over time, other molecules primarily came out of volcanic eruptions, mostly nitrogen. And that's what our atmosphere is primarily built up of. It's like 70% nitrogen. And eventually, over time, plants formed, and that created oxygen. And so, as life appeared, predominantly plants is what we're talking about. As you guys know, plants consume carbon dioxide and they release oxygen as a byproduct of their metabolism. And so it was the plants that actually created the oxygen in our atmosphere that later allowed animals to evolve and flourish as well. Now, we already talked a little bit about global warming. This is an interesting graph because it shows that for a very, very long time, the concentration of carbon dioxide in our atmosphere was pretty constant. You can see there's a pretty straight horizontal line here. There's some fluctuations around it, but it's very, very constant. And then around the mid-1800s, we can see the amount of carbon dioxide in our atmosphere started going up. And that's because people started burning fossil fuels. And as we talked about previously, carbon dioxide is a greenhouse gas. And so that's led to an increase in temperature and a dramatic increase in how much heat is being trapped in the earth by the atmosphere. And of course, the danger is that if this is left unchecked, if it continues on as it is, that will lead to very catastrophic circumstances. So there are a lot of people in the world that are very concerned about the effects of global warming. These effects can include things like rise in the sea level. And if you live on a coastal area, and a lot of people do, where you live may not be livable in 100 years. And so that's going to cause a lot of economic devastation. We're already seeing much more severe weather patterns than have been seen historically. We're going to see more hurricanes, stronger hurricanes, for example. We're already starting to see that. It's going to continue as time goes on. You're going to see crop failures as climate zones change. That's going to lead to famine, and as you're going to have refugees, and when you have refugees, that leads to diseases. It's really a bad problem. It's going to lead to an expansion of deserts. That's called desertification, which sounds fun but is not fun, because where arable land turns into desert, that means you can't grow food there anymore, and that creates even more problems. So there are lots of dangers of global warming, and that's why a lot of people are pretty freaked out about it. Next, we want to turn from the Earth's atmosphere to the structure of the Earth itself. And in particular, we want to look at the interior structure of the Earth. Now, one of the ways that we can probe that is by analyzing the waves, the sound waves that come out of earthquakes. As the sound waves from the earthquakes pass through the Earth, they interact with the Earth and they change. And based on how those sound waves change, we can actually infer a lot of things about the structure of the Earth itself. Now, in order to do that, we have to understand that there's two fundamental kinds of waves. One kind of wave is called a longitudinal wave. And with a longitudinal wave, the motion of the particles in the wave are moving along with the wave. So if I have my hand here and I'm shaking this spring back and forth like that, the waves are going to travel towards the wall. And you can see if I just shake it one time, I'll get a pulse, and that pulse will bunch up here, and then around the pulse it spreads out, but that pulse will actually travel to the wall. And if I keep shaking it back and forth, I'll get multiple pulses going to the wall, and that will be that kind of wave, and that's called a longitudinal wave. Now, when you're talking about sound waves, longitudinal waves are sometimes called pressure waves or P waves. And so this kind of wave is known as a P wave. Now, the next kind of wave is called a transverse wave. With a transverse wave, the thing that's shaking the string, in this case, that's making the wave, the shaking is at a right angle, or is transverse to the motion of the wave. So if you shake on the rope up and down, the wave is still going to travel towards the wall, but the shaking is up and down, the wave motion is left to right, so the motion of the wave is perpendicular to the shaking. In the longitudinal wave, up above, you can see the shaking is in the same direction as the motion of the wave. And that's really what the difference between the two types of waves is. Now, when you're talking about sound waves, transverse waves are often referred to also as shear waves. And sometimes they'll see them referred to as S waves for shear waves. So the big takeaway here is that there's two different kinds of waves. There are transverse waves, or S waves, and there are longitudinal waves, or P waves. And they have fundamentally different characteristics about how they move. So why is this important? It turns out that shear waves can't travel through liquids. And so if you have an earthquake, the earthquake generates both kinds of sound waves. It generates the P waves and the S waves. And as those waves travel through the mantle, which is rocky, they both will arrive at different places, and you can know that the sound waves have traveled through rocky material because both types of waves are still there. But if the wave hits a liquid material, that wave will suppress the shear waves, and only the P waves will be able to travel through them. So over here, when you receive the vibrations from the earthquake, you'll only see the P waves, you won't see the S waves, and that tells you that those sound waves have to have traveled through some liquid material. That's how we know, based on the patterns and the paths that these sound waves take, that there is a large liquid region near the center of the Earth, and that's why we say that we know that the Earth has at least in part, a liquid core. And this region where you can only see the pressure waves, the P waves, that's called the shadow zone. And so by looking at the size of the shadow zone, we can infer how big the core is, and we know that it has a large liquid component around it. Now, when sound waves travel through materials, the speed with which they move and the way that they change direction as they go from one material into another material depends on the density of the medium in which the sound wave is traveling and also the temperature of the material in which the sound wave is traveling. And so by analyzing those sound waves, we can also infer a lot about the density of the materials that make up the Earth's interior as well as their temperature. And you can see these graphs here. This is basically matching up to the picture of the Earth here. So you can say right here is where the Earth starts. This would be the ground. And as you sort of burrow in towards the center of the Earth, you can see the density of the mantle is increasing. And then once you get to the core, it jumps up dramatically. And it continues increasing to the center. Now, when you're at the center of the Earth, and then you start going towards the other side, the density starts decreasing. And then once you leave the core and you get back to that rocky mantle, the density drops back down. So this graph is showing you how the density changes. The graph below shows you how the temperature is changing. And it's interesting that as you go towards the center of the Earth, the temperature increases. And the temperature at the very center of the Earth is about 6,500 degrees, Kelvin degrees. And that's very similar to the temperature of the surface of the sun, which is actually kind of startling if you think about it. The surface of the sun has essentially the same temperature as the interior of the Earth. Now, of course, the center of the sun has a much, much higher temperature, but it's still pretty breathtaking that the core of the Earth has the same temperature as the surface of the sun, or at least pretty close. So these are some things that we have been able to deduce about the interior structure of the Earth. Below the Earth's crust is the rocky mantle, and the mantle is much less dense than the core of the Earth. The core is made out of metals, predominantly iron and nickel. And one of the interesting things about iron and nickel is that those are two materials that are capable of becoming magnetic. So the fact that the Earth has a large core made out of iron and nickel is one of the reasons why the Earth has a magnetic field, which we'll talk about later. Now we know the outer part of the core is liquid and the inner core is solid, and that's due to the immense amount of pressure at the center of the Earth. Even as hot as it is down there, the pressures are so great that it has to be solid. Now, we know about the composition of the mantle because of volcanic eruptions where some lava comes from, and that has enabled us to analyze what the mantle is made out of. Now, when the Earth first formed, it was probably a big molten ball of goo, and it remelted over time because there was a period early in the history of our solar system called the Great Bombardment Period, where comets and asteroids, things were constantly pummeling the surface of the Earth, and those collisions created so much heat and so much energy that they basically kept the Earth melted. And while the Earth was predominantly in a liquid state, the heavier things like iron and nickel, they sank down towards the center. That's how the core formed, and that's going to be something that's important for us to understand later when we talk about the formation of the Earth's moon. Now, one of the things that you may wonder is, why is the Earth's core so hot? And that's because there are also a lot of radioactive elements down in the Earth generating energy. You know that radioactive materials, for example, can be used to make nuclear bombs. Well, that energy can be released more slowly, and that's what's creating a source of heat for the interior of the Earth. So what does it mean exactly when we say that a material is radioactive? Now, you might remember from your high school chemistry classes that there are a certain number of elements, and elements combine to form all the different possible chemical compounds. But the basic building block of all chemicals are fundamental elements, things like hydrogen and nickel and iron and carbon and oxygen and all the ones you've heard about. Now, what is it that makes something one element or a different element? That's the number of protons it has in its nucleus. That determines whether it's carbon or oxygen or fluorine or whatever. And every element can have different versions of that element with different numbers of neutrons. And an element that's the same material but that has different numbers of neutrons in its nucleus is called an isotope. And some isotopes of some materials are unstable. And when they're unstable, they basically emit things in order to stabilize, and that's called a radioactive decay. And it's dangerous because sometimes these things being spat out of the atoms come at very high energy, and if they collide with you, they can actually damage your body and cause all kinds of problems. But the key thing that we want to talk about in this slide is that when you have a radioactive decay, that's essentially a transformation. The element is transforming into some other element in order to stabilize its unstable nature. And so you'll have a material transform from one material into another material, and it takes time as this occurs. So when half of the material has been transformed from one to the other, that period of time is called the half-life. And so that's one of the things that we use to characterize a radioactive decay. It's called the half-life. And so the half-life is basically just the amount of time it takes for half of a radioactive material to decay into some other material. And so if you go for a period of time, if I go from here to the period of time that's the half-life of a particular material, that means that one half of the original material is remaining and the other half is the stuff that first material decayed into. If I go another half-life, from one half-life to two half-lives, well, we had half of the original material starting with, and then we have another half-life. One half of that will leave us with 1/4 of the original material. And every time that you have another half-life, the amount of original material goes down by 2. So after the next half-life, you have 1/8, then 1/16, then 1/32, and so on. And so the period of time that it takes for material to essentially completely transform can be characterized by the number of half-lives that have gone on. This is very important because these kinds of radioactive decay processes let us determine the age of rocks. If you have a rock that has radioactive material in it, you can look at how much material is there and how much of the stuff that material decays into is there. And based on that, you can determine how many half-lives that material has gone through. And if you know what the half-life of that material is, you can tell how old it is. This is a process called radioactive dating. And basically, when you have radioactive elements that have decayed into other things, you can tell how old those rocks are. And because some of these materials have very, very, very long half-lives, we actually know how old the Earth itself is. And current understanding is that the Earth itself is about 4.5 billion years old, which is That means that our planet has been here for quite a long time.